Pleasant day to everyone. Today we are going to discuss part 2 of Module 2 Unit 1 of CE 4 to 11, Transportation Engineering. So in this lecture, we are going to discuss the different variable relationships that would define the traffic flow of a transportation system.
As we have discussed in the first part of Module 1, we have three major variables that would define the traffic flow of a road section, and that is our flow rate, speed, and density. And for the three major variables, each of them will have relationships with each other. And using a dimensional analysis of the units, it can now show that the flow rate or your volume is simply a product of the density and your space mean speed. So with that, we can now have our general equation for all of our computations later on for traffic flow as Q equal to K times U sub S. And with this, the relations now between the three important or major variables for traffic flow may be said as observed or empirical, meaning the relationships now will be defined based on what is seen or recorded based on our observations. So the first relation that we are going to discuss is the speed-density relation. And we can define the relation in terms of a graph. So for our vertical axis, we have your U sub S or your space mean speed. And for our horizontal axis, we have your density or your concentration. So basically, the relationship between speed and density will be an inverse relationship and is a linear relationship. So from this graph now, if we are going to take the y-intercept, we will be arriving at your U sub f or what we call your free flow speed. So as we have defined in the first part of Module 2, Unit 1, free flow speed is that speed that we achieve if the density is equal to 0 or near 0. And then for our x-intercept, this is what we call your k sub j or our jam density. So the jam density based from this graph is simply the density achieved when the speed is equal to 0, meaning there is no movement or there is very slow motion or flow of the vehicles. And the relationship between the speed-density relation will now be defined by the equation U sub S is equal to U sub F times 1 minus K over K sub J. So the derivation now for the relationship of speed and density will be taken from the linear relation. Therefore, we are going to apply the equation of a line. In this case, we'll be using the intercept form, which is x over a plus y over b equal to 1, wherein x will be our density, y is our u sub s, a and b are our intercepts, a is the jam density, and b is our free flow speed. So substituting now these variables in the equation will now arrive at k over kj plus u sub s over u sub f equal to 1. And expanding this equation will now arrive at our equation defining the speed-density relation. So next relation that we are going to define is the volume-density relation. So again, we will represent this through a graph with the y-axis as the volume and the x-axis as the density. So the relationship now between Q and K will be a parabolic relation. And from this graph, the maximum point now of our curve is what we call your Qmax, or maximum volume. And this maximum volume now will usually happen at what we call your K sub m, or the optimum density. So the relationship between volume and density will now be defined by the equation Q is equal to U sub F times K minus K squared all over Kj. And the derivation of the relationship will be taken from our general equation, which is Q equal to K times U sub S, and our derived equation for the speed density relation. So substituting now, U sub S equal to Q over K to our speed density relation. We now get this equation. So expanding this, will now be arriving at our volume density equation.
So the last relation that we're going to define is the speed-volume relation. So again, we'll be representing this relation through a graph. We have the vertical will be our space mean speed, horizontal is our volume. So almost the same as our volume density relation. The speed volume is also a parabolic relation, but it will now be opening about your y-axis. So taking now our y-intercept, that will be your free flow speed, and the maximum point along the x-axis will be our Q maximum, and that will usually happen at our optimum speed, or half of the free flow speed. Okay, so the speed volume relation is defined by the equation Q is equal to Kj times U sub S minus U sub S squared all over U sub F. So the derivation of the speed volume relation is almost the same as our derivation for the volume density. We are still going to use our general equation Q is equal to K times U sub S, and our speed density relation. So with this, we'll now be getting the value of Q in terms of Q over U sub S. So substituting K now in the speed density relation will arrive at this equation. Expanding this one will now be arriving at our speed volume relation. So if we're going to compare now the three graphs that would define the relationships of the three variables side by side, okay, so we'll have this arrangement. So as you can see, we have your Kj for the speed density and the volume density relation, and we have here your U sub F for the speed density and the speed volume relation. Okay, so extending now our optimum speed and your optimum density, it will now be intersecting our linear graph for the speed density. So if I will now make that as a single graph, or make the U sub SKJ graph larger, okay, so we have here your free flow and we have your jam density. So the intersection of your U sub M and your K sub M here, and the shaded area will simply represent what we call your Qmax, or the capacity of the road. And for Qmax, we can now compute this simply as U sub m times K sub m, which is the same as your Kj divided by 2 times U sub f divided by 2. Okay, so take note that U sub m and K sub m is what we call your optimum speed and optimum density, or the critical speed and critical density respectively. So your optimum or critical speed or density is simply defined as the speed or density that would exist in your road section when the traffic along the lane or along the road is flowing at its maximum. So the maximum volume is your capacity. So to understand variable relations, let's have some example. So let's say the data on density and speed were obtained from a four-line, two-way rural highway in one direction only. So the density together with the speed are recorded here. So using now our variable relations, we now determine the relation between the density and the speed and the free flow speed and jam density of the road and the maximum volume or the capacity. So for our solution, we'll now be applying these equations. So we have U is equal to A plus BK. In U is your speed, K is the density, and A and B are constants. And these constants now will be computed by the equation. A is equal to the average or mean of U minus B times the mean or average of K. So as you can see, this equation is taken from this general equation. So B now is equal to the summation of Ku minus n times Ku all over the summation of K squared minus n times K squared. So if you can see, this would likely be similar to our standard deviation or our variance equation from probability. So for your correlation, you always check that the value of R will be almost equal to the absolute value of 1. So R now is simply computed as B times S sub K over S sub U. So Sk and S sub U will almost have the same equation. The only difference is that we use the density for Sk and the speed for S sub U. So we have summation of the quantity K minus K mean square divided by n minus 1. So always take note of these equations. So from here, we can now solve for our values in a tabular form. So we are given the K values and the U values. So let's solve first for the sums of K, 303.2. For the sum of U, we have 170. For the mean values of K and U, for K we have 83 and for U we have 42.5. So just complete the table for KU. So that's the product of the values of KU. So we have 3,375, 1,275, we have 1,420, we have 3,000, we have 9070. Then for K squared, that will be 5625, 225, have 2164. Then we have 10,000. Okay, for the sum, it will now be 36,014. Okay, so let's solve for the individual values of K minus, so K minus their average quantity squared, so that will now be for value 1, 64, then we have 4624, 3481, 289, okay, and then for the sum, that's 8458.
for u, individual values of u, minus bar u squared. So we have for value 1, that will be 6.25, 1806.25, 1056.25, 156.25. So our sum is 3025. Okay. So for our solution, take note from the table, bar k is 83, bar u is 42.5, summation of k squared is 36014, and summation of k is 9070. So applying that in the equation of b, we'll now have 9070 minus our observations 4 times 83 times 42.5 divided by 36014 minus 4 times 83 squared, giving us a value for b, which is equal to 0.5959 negative. Then we apply our equation for a. So bar u is equal to 42.5 minus our computed b, negative 0.5959 times bar k, which will give us a value of 91.96. So using now your relationship between the speed and density, we now have u is equal to a plus b k. So u is equal to 91.96, our computed a, minus our computed b times k. So this equation now will define the traffic flow of the road section under study. Okay, so for free flow speed, that will now be uf, that is when k is equal to 0. So just substitute k equal to 0 in this equation. So the free flow speed will simply be 91.96. And then for your jam density, k sub j, that will happen when u is equal to 0. So substitute u equal to 0 in our derived equation. That will now be equal to k sub j is 154.32 vehicles per kilometers. And for our q max, that will simply be the half of u sub f times the half of k sub j, or that's your u sub m times k sub m. And that will give us now a value of 3547.82 vehicles per hour. Okay, so for your references, please do check the Fundamentals of Traffic Engineering by Ricardo Sigua and the site given. For your evaluate activities, please answer the elaborate problems found in your module and upload the PDF file of the solution in our classroom. So thank you for listening.